Okay, I want to explain here the idea of a bivariative normal. You should have a very clear picture of what is going on. So the best way to understand this is to do some arts and crafts. What you should do is like this. Take a cardboard and draw very roughly such a curve, like a normal curve. Now, what you should do is you should draw this one inside the other one. Now, if you understand, all of those have exactly the same variance because they're the same. The variance is described by how wide. This is just, everything is just shrunk, smaller or bigger, but it's not, the variance is the same. If you understand, the variance shows how much the bell is flattened. So basically you have here a lot of curves that all have the same variance. It's important to understand this. Now, when you did this, you have this drawn on paper, just cut out all these shapes, and so you have like a mother, a grandmother, a son. This is the tiny baby of the family. You have all these things, these cardboard standing. Now, make them stand on the table. You make the mother, the grandmother, and then you take let's call them the oldest son, is not exactly close to the mother. He is stepping forward on the table a few centimeters. The third son, even more. The baby, even more. That's how, this is the general outlook of what a bivariative normal that is dependent. Please do it. It's so important. You'll get a different feeling of the whole thing. So again, the idea is like this. Let's use the famous, everybody uses that, weight and height. That's what everybody likes to use. That's a typical example where there's two things here that are normal distributed. Weight, there's a certain average weight of an American, then there's the average height. But obviously it's not independent because we can say, at least it could make sense that the more height, the more you weight, or the more the weight, the more the height, something like that. It goes somehow together. So let's interpret this in this model. The one that you place, the biggest one that I call the grandmother, that will be describing the average. That will be the slice that tells you the average height. Let's say the average height is 5'11", so that is the average height. That's the slice, the biggest slice. Next, now this slice obviously has a lot of different weights. So when you put it on the table, this slice is the 5'11" slice, but it is ranging on the y-axis all the different weights that are possible in this. I want to make sure you understand what I'm talking. You put it on the table, so one of it is facing you, your stomach, the other one is facing away from you. That's how you put the piece of cardboard. This, I'm talking now about you taking now the grandmother, the biggest slice of this bell curve. You're taking the biggest card, you're placing it in front of you, like this, the one that's towards your body, and then one most away from your body. So first of all, this slice represents all the population that is average height, 5'11". But within this, there are different weights. So the ones that are the most away from you, from your stomach, that is the ones that are the most weight, the fattest. The one that's closest to you, that's the lower one in the y-axis, is the other skinnier ones. And the one that's exactly in the peak, the center, that is the average weight between the guys that have 5'11" height. Okay, this is this nice big slice. The next slice is a little bit smaller. That's we call the child. That slice is pushed slightly away from your stomach, a little bit away from your stomach. Not you push it, you put it, the first one close to you, the second slice a little bit away from you. And again, this slice represents the guys that are 6-footers. So obviously this slice is a little bit smaller because there are not so many 6-footers around, right? So it's smaller. This slice is not such a fat, is not so tall. He's not the grandmother slice. Let's call him the father slice. Now this slice are all the 6-footers. Now it is away from you a little bit. Why? Because here by the 6-footers, the range from the weight starts a little bit further. It's 6-footers are naturally way more, so by them the average weight is further up in the y-axis. The variance is the same. We're assuming that it's not the idea, the basic shape is the same, the variance is the same, just it's a smaller slice because there are less people that are 6-footers, and the average weight of the 6-footers is a little bit further on the y-axis. It's, let's say, not 180, it's 190 pounds. Next case. Now we take the third slice, even smaller slice. That's we call the second child. The second child slice. That's also a cardboard, the same bell shape, the same variant. He's even further away. These are the ones that are 6'2". All the guys that are on the 6'2", 6 foot 2 inches. They are even further away. They're the smallest slice. They're further away. Means you say the average point of the weight is further. So on the fifth slice, finally, are the people that are the tallest, let's say 6'5" or 6'6". They are the smallest amount of population. The average weight from them is very far away from your body, from your stomach, and then you have an idea what this is all about. So let's sum it up. Just put it on the table, you get a feel of it. Each one is following a normal distribution. It means that's what we call in the fancy mathematical language, given a certain certain x, because it's each slice is certain on a different point on the x-axis. Given x is equal to something, let's say given x is equal to 5'10" or 6 or 6'2", given that y has normal distribution with the variance is the same, but the expected is different. Next quality, the marginal distribution. I have to stop here because it's 10 minutes. I'm sorry.